Okay, so last time we started talking about, well, we talked about Vivado, right? And then up through simulating. Today we're going to move back to pen and paper methods for designing circuits. So normally what we would do, right, is if I gave you a problem, you would write out the truth table, write out the minterms, and then start simplifying down and get the circuit. But you can imagine how difficult that gets if you have, say, even 4 terms, right? So, sorry, 4 input variables, which means 16 potential minterms, and 5 variables is 32 potential minterms. That gets tedious to write out and insanely difficult to simplify. What if there was a tool that we could use that makes this easier? Well, I mean, unsurprisingly, there is, and they're called K-maps. Carnot maps. Carnot. I don't know how to pronounce it, but we just call them K-maps. And what a K-map is a visualization of a particular method for simplification. And I'm going to go ahead and illustrate that simplification and why K-maps work. So let's say that you have an expression that looks something like this. And so on, right? Say we have more minterms than that. But what I would look for in order to simplify this is 2 product terms that differ by only 1 variable. Because what that means is it's easy to factor. So, I mean, 1 variable here, this term and this term, these 2 product terms differ only by x2, because it's x2 bar and x2. So if I want to factor those, it's really easy. I just take out the x1, x3 bars, and I end up with x2 bar or x2, which, as we know, is always true. One or the other has to be true, right? So it simplifies down to x1 bar, x3 bar. So we take 6 variables and 2 product terms and turn it into 1 product term with 2 variables. And we can do that all the time, right? That's what we're looking for in the simplification. This is theorem 14a that just says that I can do this, essentially. Now, because these are just minterms, this happens reliably all the time. And if we were to go about it, a lot of times the simplification involves like adding an extra of a term, right? Because if I say something like A is equal to A and A, it's fine. So if I had x1 bar, x2 bar, x3 bar, x1 bar, x2, x3 bar, and then I had a third term of, here we go, this. Say that was my whole expression. If I wanted to simplify this, I could just add an extra of this first product term and use it to simplify this one. Does everyone see that? If I could just add an extra one in order to help simplify here. Does that make sense to everyone? Okay, good. Because that's going to come up. All right. But what we want to do is find a quicker way to handle this. And that's K-maps. So what a K-map is, and I'll start with the simplest version of it essentially, is if I have a truth table like so, then this minterm, right, is min 0, min 1, min 2, min 3. I can represent these into a map, a K-map, that looks like this. The way I fill this out is if I take A0 and B0, this is M0. So if that minterm is 0, I would put a 0 here. Okay, 0, 1, 0, 1, M2, oops, sorry, 0 index, M1, 1, 0, 1, 0, and then finally 1, 1 is the bottom right corner. Sorry, M3 is the bottom right corner. So 1, 1, M3, bottom right. So this is how we place things into a K-map. Well, what does it do? Well, what it means is that all of these terms, if they share a border, are what we call logically adjacent. Now, that's just a fancy term for saying this is true. They differ by only one minterm. So we have this nice visualization of potential ones and zeros that I can easily see a relationship between. A, B, 0, 1. Now, let's say that I have a function f, and I want it to be, what's a good one? A NAND gate? Ooh, what's correct? NAND gate, there we go. Sorry, I screwed up my honey, or my tea this morning, so I have the honey, and my voice is gonna be a little wonky today because I'm running out of it. Okay, NAND gate, right? What I need to do then is fill in this K-map. Okay, so I've labeled where the minterms go, and I can just fill them in. 1, 1, 1, 0, like such. All right, what does this do for us? Well, now I have two groupings of 1, two things where they are logically adjacent, two ones that are logically adjacent. Okay, let me pull out a different color real quick. This minterm and that minterm are logically adjacent. That means they differ by only one product variable. Also true here. And this is just a visual representation of 14a. Okay, so now all I have to do to write the simplified form of this is to find what does that circle mean. Well, I look for what doesn't change in the A and B, in the variables. What variable doesn't change? Well, for this horizontal implicant, B doesn't change. And it's a 0, so it's B bar. In this one, A doesn't change. So that means I have OR, and the A is a 0, A bar. So what this expression is saying is if I have either a B at 0 or, B is equal to 0 or A is equal to 0, then this function is true. Well, that's true. Right? This truth table shows that. If either A or B is 0, right? So this is our tool for visually creating simplified versions of our equations from a truth table. This is a K-map. We can expand this really easy. If I need a third variable, I can do something like A and B double the width of it and have minterms. So I have 0, 1, 2, 3. Now I need to add 4, 5, 6, and 7, right? Minterms. But there's a trick with them. Because what you'll notice, 0, 0, is actually that minterm 4 is not logically adjacent to minterm 3. And this is a problem. The reason is because I'm changing two of these variables at the same time. If I'm only changing one variable as I go down, all is good. If I'm changing two variables at one time, all is not good. We know this from the first one because M1 and M2 are not logically adjacent, right? M1 is here, M2 is here, that's diagonal, they don't share a wall, therefore not logically adjacent. So how do we fix this here? Well, we use something called gray code. And it's a method in counting in binary that we only ever change one bit at a time. So I'll keep C, the horizontal or the vertical, the same. And then I have 0, 0 as my A, B, right? So this is A, this is B. Then I have 0, 1, and then 1, 1. So I've gone from 0, 1 to 1, 1. I've skipped a number, but this is just gray counting, gray code, okay? And then 1, 0 is here. So now it looks like 0, 1, 2, 3, where they originally were. Then the right column gets M4 and, yes, M5. And the third column gets M6 and M7. Now they're logically adjacent. Now this K-map works. And I can go ahead and create an example. So I strongly recommend writing out this way all the time for the first while. Eventually, maybe you can skip the labeling, but you can never skip labeling the variables. You always have to say what position they're in, because K-maps can end up with multiple versions of the minimum solution. There is not just one answer. You can come to different answers. So I need to know how you got to it. So when I'm grading your exam, say I can at least give you partial credit if you go wrong, so I can see why. Okay, so I could write out a truth table for this, or I can just fill in ones. Okay, here's a good example. So this one, 3-variable K-map. I could go back and fill in a truth table just using this. Because there's 3 variables, I know there's 2 to the 3 rows, 8 rows, and I know that they correspond to these minterms. So 0, 0, 0, if I write it this way, okay, 0, 0, 0 is a 1, so F is 1 in this case. 0, 1, 1 is this, 0, 1, 1, it's minterm 3, right? And I can go back and I could build out this truth table from the K-map. They're linked. Now, 2 ways to do this. You can just write only the ones and assume that everyone else is a 0, or you can explicitly write out the zeros, your choice. Because if it's not a 1, it's a 0, right? All right, so now let's go ahead and draw some circles. Moreover, let's give the circles a name. These circles are called implicants. Now, an implicant is a circle of ones. It is a valid circle of ones. What does it mean to be valid in this case? It means it has 2 to the n ones that are circled as either squares or rectangles. So no weird shapes that kind of loop around things. They have to be nice, smooth squares and rectangles. We'll see lots of examples throughout today. So 2 to the n means you can have 2, 4, well, 1, 2, 4, 8, 16, and so on. So I can't circle 6 of them together. I can circle 4, I can't circle 6. So the circles, again, are implicants. Now, there are a couple different kinds of important implicants. Now, you'll hear the term prime implicant. A prime implicant is a really complicated thing to wrap your head around, and it's essentially the list of all implicants that are necessary to cover the K-map. Cover meaning I have all ones inside a valid implicant. I'm not going to let you worry too much about prime implicants because what I want you to focus on is essential prime implicants. What essential prime implicant is the idea that it is necessary to cover a particular one. It is the most simple implicant necessary to cover a one. And we'll get more over what that means later. But here, an essential prime implicant is something like this. Because the only implicant that I can get one in, this one, is this implicant. It has no other neighbor to circle with, so this is a necessary implicant. I have to use this one if I want to end up with a minimum expression. There's no other choice. Now this guy has no neighbors at all, so 1 is a valid choice. It's all by itself. It doesn't really help with simplification, unfortunately, but this is also essential prime implicant, EPI. Now, this guy, he looks alone, but what you'll notice is by counting in gray code that 0, 0 and 1, 0 are actually logically adjacent. So what I can do is that. It wraps around. Okay, so let's go ahead and write this function. So let's start with the guy all on his own. Since there is no other implicant, he's going to have 3 terms. There's no simplification happen. He has to have A, B, and C. So A, B, C, and then which ones are barred? Well, it's A bar, B, C. Because the 0, 1, 1 is its midterm. So A bar, B, C is its midterm. Similarly, let's go ahead and look at this vertical midterm. Remember here, we're looking at what doesn't change through the circle. Well, neither A nor B change because it stays in that same column. So I have A, B bar. Okay, this last one is a little bit trickier to see because it wraps around. And we're going to see that what doesn't change. Well, we see C doesn't change because it's horizontal. So C is going to stay the same. But one of either A or B changes, right? So A is a 0 here, a 1 here. It changed. That's not good for us. So let's look at the B. 0 here, 0 there. We use a B. So that means it's either B, C, and we check the bars because 0, C is in the 0 column. So that's C bar, and B is also a 0 when it doesn't change, so that's also B bar.
So each term is going to be like the number of total variables minus the power of 2 that the implicant is of size. So if it's 2, then that's 1, so there's 3 variables, so it ends up 2, right?
Yes.
And then if you have 4, that's 2 to the power 2. And if you have like 4 variables, that's 4 minus 2, and you get the size of 2.
Yes, yes. So the bigger the circle we get to draw, the fewer number of variables we'll have in our product term that is associated with that implicant. So let's change this just a little bit. No, leave that one. Add this one. So this one, min term 0, 1, 2, 3, is no longer an island. It now has a shared implicant. So I can circle that way. But I'm also going to redraw this implicant. Actually, both of these implicants. So what that extra one has done, again, I can wrap around. And 2 to the 2 is 4, totally valid. Get 4 ones. So now I'm going to have even fewer variables in my product term for that one. Well, let's just rinse and repeat. We've got C doesn't change here, and neither does A. A is a 0, C is a 1, so it's A bar C. Or I have one other implicant. This one gets a little bit tricky. C changes, right? 0 to 1. A changes, B doesn't. So B is the only one that doesn't change, and doesn't change as a 0. B bar. Both of these implicants are essential prime. This one is required to get this one, and then the other ones can be included in this fairly large implicant, making it essential prime, because it is required in order to have the most simple function. If I don't have that big one, it's not the simplest form it can be. Okay, there is another vocabulary term that I'll create a new K-map for. So the way I draw these, if you guys want to know, is I just split them in half and then half and half so that it's easy to draw and they're at least fairly consistent. I'm terrible at drawing, so that's the best way I've found to pull it off. Okay, so let's have this. Now, essential prime implicants here. This one has nobody else to pair with except for this one. That's essential prime. This one has nobody else to pair with except for this one. That's essential prime. This one is okay to share with another implicant. Just like I shared this one at M1, I can share this one. But it is not essential in either direction. So this is what I call selective prime. I get to choose whether to use that implicant or that implicant. That makes sense? So I get to select which of those I do. They're not essential because either one could be true. Now, if you chose either one, it's the correct answer. It ends with a different answer, but it just means that it has different ways to get to the minimum function. That's okay. So that's selective prime versus essential prime.
And both of the terms that you would get with either one, both of them would be valid, either one of them.
Correct. What this represents is adding an extra, the overlap. Sorry. If I have the overlap, it represents adding that extra term inside of the math that we did before, right? In order to keep simplifying. That's all it is. I'm adding an extra term that's redundant in order to simplify when I share. Sharing is okay. That's why I showed you the math at the beginning. All right, let's go ahead and address what happens if I want to use 4 variables. And I'm going to write this one a little bit different. And I'll turn this into a truth table in just a second to explain why I do this that way. All right, what example am I going to pull? After this one, I'm probably going to start filling in the zeros just to speed it up, but for now, I'll hold it. Okay, and again, I strongly recommend writing out what the 0 patterns are. There is another way to do this I don't particularly like because it takes me longer to draw and doesn't help me. It helps some people. So I know that this is all BA on the horizontal axis. And then I can say it's 0, 0, 0, 1, 1, 1, 1, 0. That's the same as saying 0, 0, 0, 1, 1, 1, 1, 0. I don't like this way, and I always screw it up. So I'm going to stick to the zeros and ones. All right. Now we start looking for the implicants. So
I have a quick question.
yeah.
So the B and A switched when you're doing 4 terms, because before it was A, B, and now.
So you don't have to switch it. This is an option. So if you were to write A, B, C, D by flipping them, that's valid as long as you fill them in the right spot. So part of the reason that I like to do this is a lot of the times when I write my truth tables is, to me, the D should be the most significant bit. So I would like my truth table to look like this. A, B, C, D. And then what that means is if I have, well, 0, 0, 0, 0, this is still M0. 0, 0, 0, 1. So 0, 0, 0, 1. Is that right? Did I screw that up somehow? Oh, A. A is 1. Sorry. So 1, 0, 0, 0. That's M1. And then 0, 1, 0, 0, 0 is here. So this is M1, 3, and this is M2. So it's just a different way of representing it. So if I were to flip the A and B and the C and D, then it would be columns instead of horizontal. Still valid. You'll still get the right answer as long as you're consistent. I do see students mess this up where they write one and do a different one. So here's just illustrating that either way is fine. Just keep track of what you've done. Okay, where to put the orange marker? Let's find some implicants. Now, I'm gonna, for the people that are taking notes, I'm jumping ahead to number 6 and 7 on this one, just as I talk through. So there is a procedure that we use in order to find them. Now, the book's procedure says the following. generate all prime implicants, find the set of essential prime implicants, then add any non-essential prime implicants to complete cover, where cover is completed when you have circled all the ones. Now, I went through that fast. It's in the book. You can find it. There is a much more intuitive way of doing this, which is just look for the biggest circle that you can draw. If you can start there, you're most of the way done. The trick is finding it. Who here, what is the most number of ones that I can put inside a single implicant? 4, because of the wraparound. And then all I have to worry about is cleaning up the rest of the ones the best way I can. Like so. So there's nothing really that different between here and the last K-map, right? The 3-variable K-map, it's just more things that you might have to circle. We write the function the same way, where we find the variables that don't change. Take a minute, actually, write down this function.
So good question. So we don't have to do the selected one on the bottom one because we already are forced to do the top one. Right?
Yes, exactly.
So we don't have to connect those two.
Correct. You do not need this implicant. If you were to, it's still valid. It's still a true function. It just isn't the minimum. And in fact, it's a good question because later we will do this on purpose. We will add that extra one because it adds a level of robustness to the circuit that we don't have here. And we'll get into it, but it involves the timing of gates. We'll explain later. So don't worry about that, but do know that that is actually an important kind of observation. There's a risk in having adjacent ones, adjacent minterms that don't share an implicant. That does cause a risk in the circuit. But we'll deal with that towards the end of the semester. Okay, so let's go ahead and who wants to yell at me the first implicant? No one's on.
Not
ECE.
So raise a hand. Let's get a hand somewhere. What do you got?
not AD.
Not A, D. So that's the 4. And so what we see here is A is here, A, in that case, both cases it's A bar. So that's not A, doesn't change. And then on this side is D, doesn't change. That is correct. Now you have to be careful to not flip them in your head, right? Because it would be really easy to accidentally write not BD if you weren't paying attention to how I wrote this K-map. All right. What's my next midterm?
Got B, C, and not D.
B, C, not D. Let's check that. So B is here, 1, 1. So it's 1 is a true, there's no not on it. That's correct. And it's in this row, so both C and D is knotted, C is not knotted. That's confusing, but it is correct. Everyone see that and agree? It's highly likely that I will screw at least one of these up throughout the class, so don't be afraid if you see something weird and ask a question.
Question, and it
Yes.
might not be important, but is this M3 or M2?
This is M2, and it is important. So it goes 0, 1, 2. Oh, shoot.
It should be 3.
Aha.
Okay,
No, good question. 3, 2. Yeah, 0, 1, 2, 3.
okay.
4, 5, 6, 7.
Well, it jumps to 12.
Yeah, yes. You want, let's just write it out nice and big for everyone to see. This is not bad. So when you take the exam, I allow open notes, open book. I highly encourage you to make a note sheet because that's a good just help of studying. Even though you can open the book, making a note sheet is good. And having just this on there can be really helpful for some students. So consider it. Okay, so I'm going to erase these out. Okay, let's make up a new one. Yes, I like this example. Okay, so I want you guys to take a moment to start finding the implicants. And then in just about 30 seconds, I'll tell you how many implicants you should have. All right, who's feeling clever? Who thinks they know how many implicants is required?
Well, you can do it with only 2, and then there's 4 total, but the other 2 are redundant. So there's a group of 8. You do the bottom 4.
Yes, so the one that would look appealing is this 4,
And then jump.
but because this row and that row are logically adjacent, they can share. And 2 to the 3 is valid, right? 8 is valid. So that is an acceptable implicant. But then we only need one more implicant, right?
The square, yeah.
The square. I've completed cover with the minimum number of implicants. Therefore, I will end up with the minimum circuit.
Sorry, would you need to get a rectangle by connecting the top 2? I mean, could you do that?
So these, no, you cannot, because 2, 4, 6 is not 2 to the n.
Oh, okay.
And we'll do another example that highlights this as well, right after this. Okay, take a moment, write down what this function is. All right, so again, just looking for things that don't change. Let's start with the AB column. Well, if I'm spanning all of A and B, the whole horizontal, they're going to change. They're both going to change. They have to. So the only things I could have is C and D. Well, D changes from 0 to 1. The C doesn't. And it's a 0, so it's a C bar. Here, the 4 terms, you are gonna, the squares you're gonna get like the hardest ones to follow, but again, it's the same thing. The D doesn't change, it stays a 1. And then B doesn't change, it stays a 1. So B, D, for each of your product terms, please write them in alphabetical order. Don't write DB, write BD, because it ends up being way easier for me to grade, which means I like you better, which means I'm going to go easier on you. It just happens. If I get confused, I get frustrated, and I give you less partial credit if you screw up. So I see what you did. I go, oh, they were almost there. They drew an extra 1. That's fine. But I'm gonna look at it and go, I have no idea what you did. How do I give you partial credit? And anything that you do, including just writing it in alphabetical order to make it easier for me to see what you've done, results in more partial credit on exams. No real good way to use these K-maps, is there? I give up. Let's try again. Okay, I promised you an example to highlight. Don't do 6 together because it's not valid. Okay, go ahead and start doodling in your implicants. And try and take it all the way. Try and get to the function. As a clue, you will need 3 implicants. Okay, let's make sure everyone's at least gotten the implicants right. So there's actually an interesting thing going on here because we want to find the biggest ones we can, right? They're actually all going to contain 4. So what we want to find really is the essential prime ones first. What do we need in order to complete cover? Well, we have these 2 ones that can be shared in a square. What's another one? Essential prime.
The long row or essential?
Find the essential prime one.
Those bottom 4 there?
Yes, exactly. I need this one. But now you have a choice, and that's a good call out. So you said which one?
The entire long row.
Yeah, the entire row. So this is a good selective prime, right? And it's selective prime because I can just as easily use this one and complete cover. As long as I choose one or the other of them, I've done it right. I'll get to the right answer, a right answer, but there are 2 correct answers in this one. So take your pick of those, finish off your equation. Want to give me one of my implicants into my equation?
Just one of them, you don't want both.
Just give me one of them. Just one implicant.
I got not B and not D.
Not B, not D. And which implicant is that?
I believe that is the top left.
Top left. So you're saying not B, 0, 0, not D, 0, 0. Correct. Give me another implicant.
BD,
BD. Which one is that?
the bottom right square.
The bottom right square. So here we have B is 1 and 1, stays the same, and D, 1 and 1, stays the same. Correct. Give me a third one.
The tall one,
Okay, the tall one, what is it?
ABD. ABD.
ABD. Okay, so almost. D. Does it change? It does. Because if the tall one is going the whole vertical span, D changes. So that's a one to look out for. And your verification is, if this has 4 ones in it, and this has 4 ones in it, they must have the same number of variables in their product term, which is 2. And you can kind of count down, right? If you had all ones, you would have no terms. If you had 8 ones, you have 1 term. 4 ones, 2 terms, and down on, right? Because all 1 K-map, or if equivalent, all ones in your truth table is a trivial circuit. If it's just always 1, it's not doing anything. Yeah, so great. Let's go ahead and write the third one. So this is AB. You just added the extra D, but that's okay. Because A and B are both 1, C and D both change. So the only remaining is the black square. Give me the black square implicant.
A not D.
A, not D. So A is 1s for both, and D is 0 for both. That is correct. And I'm calling you guys on at random, not to pick on you. It's to make sure that you guys are all understanding, and I see if you're falling behind somewhere. All right, let me flip through my notes and make sure I got everything. Otherwise, I'm going to just do some more good examples.
Are we gonna do where we circle the zeros and get the?
We will do that next week. So this circling the ones is giving us sum of products. We can actually switch and do the zeros and do a product of sums, but there's a little bit of a twist to it.
Just like the Morgans, right?
It's a De Morgan's, yes. And so we'll do that next week. We'll build up the complexity slowly.
Are you gonna do a 5 variable?
We will do a 5 and 6 variable, yes. So as a sneak peek, a 5 variable, I'm just going to stick another K-map to the side of this one. And then as long as my numberings are correct in gray code, they will be logically adjacent, including a wraparound. For 6 variable, we need 4 variable K-maps. And we assemble them in a cube, a stacked cube, and have to visualize them in 3D space, which gets really hard and fun. But we'll get there. Okay. Let me wipe this away and we'll start with a new example. So this next one is something I love doing on my exams. Yeah, let's go ahead and do that one. So again, just start by finding the implicants, and then in a couple of seconds, I'll tell you how many you're supposed to have, and we can revisit, make sure you got them right. Okay, so just a heads up, I count 3. And all 3 are essential prime. So the first one, vertical column, we like vertical columns because they're easy to write the expression for. The next easy one is horizontal, second row down. Where's the third one? I said you only need 3.
It's the 4 corners.
The 4 corners. All 4 corners are logically adjacent to each other because they wrap around horizontally and they wrap around vertically. I can draw a square. The way I draw that is like so.
Because the K-map's actually like a torus, right? Because like the 2 ends. bend.
Yeah, yes. Yeah, there is a 3D representation of this.
Is it Taurus?
Yes, it's wrapped around. So this is your covered K-map. Go ahead and write the function as I do it, and then check that you're right. Okay, so I guess I'll walk through the square with you guys since it's your first time following. So do we agree that these two? Get those right? I think so. Okay, so now let's see what doesn't change in this square. So first off, I'm going to start with the horizontal. B does change, so I'm looking for A, and it is a 0, so it's a bar. Now vertically, C doesn't change, D does, and C is a 0, so it's C bar. You can take it stepwise, just like that. Be meticulous with it. Don't just try and throw it down because you will make mistakes. It just happened. I think the biggest issue on any exams with K-maps is really students just rushing things and not being meticulous. Okay, let's do a whole design problem. In fact, we're going to use our lab that we did as our example. So in our lab, we have a truth table. And we have a 0, A1, B0, B1, where A and B are 2-bit numbers. And we want our function to be true when A is less than B. I'm not going to write the whole truth table because it's long, but I will give you a sampling of it. Okay, 4 variables, 4 variable K-map. I've split A into its 2 bits so that I can see them on the K-map easily. I have to choose the order in which I place A0, A1, B0, B1 on this. I'm going to provide that to you here and usually on the exams so that you end up with the same looking K-map. A0, A1, B0, B1. So that's your order. So now what I want you to do is fill in the K-map. Given the requirement that it's the K-map for A less than B in 2 2-bit numbers. So I will give you the first sample. So they're equal here, right? 0, 0 is equal to 0, 0, so it's 0. A here, 0, 1 is greater than 0, 0, it's 0. But if I go down to something like 0, 1, 0, 0, well, 0, 1 is greater than 0, 0, therefore that is what? Go ahead and finish filling in the K-map. We're going to use a K-map to design the minimum circuit to find A less than B. So I've got the, I believe, correct truth table up now, so you at least have that starting spot. Give you a second to look at that and make sure yours matches. If you see something I did wrong, let me know. Okay, so I'm gonna again, have you guys at least gotten to try and take the numbers from the truth table to the map? So I'm gonna walk through that now. And I wanna make sure that you at least tried it yourself, time's okay. All right, so once we've established which direction the midterms are going, it's pretty easy, right? So if I have, this is always going to be midterm 0, so it's easy. Then we just have to determine, is this midterm 1 or is this midterm 1, right? So here is 1, 0, 0, 0, 1, 0, 0, 0. So that is midterm 2. So now I can just start writing them. I get 4 zeros, 0, 0, 0, 0. Notice how I skip to the end row and then come back to it? That's easier for me to think that way. So again, I got those 4 zeros filled in. Now I do 1, 0, 0, 0. 1, 0, skip to the end for the last 0, 0. Now I'm going to drop down to the bottom row for the next 4, which is 1, 1, 0, 0. And then the middle row for the last 4. 1, 1, 1 at the end, 0. Yeah.
On the one that's the second term in on the second one, isn't that supposed to be 0, not 1? On the truth table.
On the truth table,
No, on the actual truth table.
Oh, the truth table.
Yeah, the second one down. Would that be 0?
This is 1, 0, and B is 1, 0, and A is 0, 1. So this is 1, and this is 2.
Okay.
So 2 is greater than 1.
Okay, I was just thinking.
Yeah, this one can get tricky. I want you to know you are not the only one to make that mistake. Basically, every class I've had of this makes that mistake, so someone does. Yeah, we're still kind of learning binary numbers, so this is a little bit tricky, but we use them a lot. All right, now, hopefully you guys have filled in your K-map for this problem. And let's go ahead and find our implicants. I called on, I think everyone is awake anyways. All right. Do you want to point out to me an essential prime implicant?
The bottom square.
No.
Oh, sorry.
I think the bottom 2 rows. The bottom 2 rows, and well, I guess bottom 2 on the right.
These 4. Got it.
Or
Yes.
sorry, on the left.
Yeah, got it. Yeah, so those are a great, right? That's our biggest square that we can possibly do. Next up, do you want to go ahead and give me the next essential prime?
So 2 on the left.
Yeah. And then our last one, right, is just the wraparound. There. This looks right? If you remember your lab, we had 3 terms. So we've got 3 implicants. We're feeling pretty good that we did this. Let's finish it off to make sure. I'm going to go ahead and say F is what I'm just going to call it, is equal to, have you guys at least tried this, written the equation? Looks like. If not, don't look up yet, because I'm just going to write the equation and then you can compare the answer. So let's find this one, which is the 1 doesn't change and the 0 doesn't change. So I'm looking at A1, B1. So it's A1 bar and B1. This guy has A0 and A1 both don't change, and they're both zeros. But I also have B0 not changing. Then the wraparound is going to have B0 and B1, and looks like A0 bar.
It's more helpful to you if we put 0s before 1s.
Yes.
Okay.
Yeah, alphabetical and numerical orders is preferred. And I'm going to try and write the exam questions to specify that. Sometimes I forget to do things, but look out for that. What I'm saying is read the instructions clearly on my exams, because there's particular ways I want the answers to be presented. Yeah. Okay, do you have any questions on this one? I don't have the lab pulled up, but that looks about right. Okay, still got some time. Great. Let me flip through. All right, something I need to mention. Your book will talk about cost, the cost of a function. Now, this is an idea that runs all throughout engineering. You're asked, what is the cost of a circuit or system? Now, we don't mean the dollar value. In this class, when you're asked what the cost is, it's something very particular. What it means is the number of gates plus the number of inputs. Now, I'm not going to test you a lot on this, but it does come up in your book. So if you're doing book reading and says this cost is less than that cost, that's what it means. They're just counting up the number of gates and the number of inputs. Now, this is confusing the first time you see it if someone doesn't explain it to you, so I'm going to go ahead and do it just so you can follow along in the book. I may accidentally assign a homework that has it in this. If I do, you can just kind of skip it, and I won't care. But I just want you to understand what they're saying. So if I have a circuit like so, okay, and I'll just call this A, B, C, D. All right, so as I said, it's the number of inputs plus the number of gates. Your first instinct is going to be 4 for the number of inputs plus 3 for the number of gates. Unfortunately, they also count the number of inputs to all gates. So I actually have to also add these two. So it's 4 here, 3 for the gates, 2 for the inputs to that last OR gate. The reason that we add that second tier input is if you end up with a 3 input OR gate at the end, that's more expensive. It costs more. If you add a third AND gate, and let's say that this is A bar, C bar. Okay. So I have 1, 2, 3, 4. I don't have to add it just because of an A bar and a C bar. We assume that we have access to A bar and C bar. However, we do still add it because it's unique input to an AND gate. Now, why did I make that distinction? Let me give you.
There would be 6 inputs.
It will be 6 inputs here, but I can do this. Let me puzzle out how to do this the best way. That doesn't quite work either. I haven't practiced these examples because they're not that important. But what this one does is still 1, 2, 3, 4, 5, 6 inputs. And what I'm really trying to get at here is you could draw this circuit this way. I don't have to count that gate because I'll just assume that I have access to B bar. So inverters are nearly free in circuit design is what I'm getting at. So this one then, B bar is 1, 2, 3, 4, 5, 6. Let me write it somewhere higher. 6 for the inputs, plus 1, 2, 3, 4 for the gates, plus 1, 2, 3 for the inputs to the OR gate. 7 plus 6 is 13. 15. Yeah.
So if you had like A just on 2 different gates, would that still be 6 inputs or would that?
It is still 6 inputs because what we're counting is the number of inputs to these gates, regardless of what they are. So the point about the B bar is that inverter doesn't need to be counted. However, if there was, say, an inverter here, they do make me count that, which is obnoxious. It's just your input variables that you don't have to count the inverters on. But this is what your book means. And in the future, in your career, you are likely to end up in a situation, especially as you get to senior engineering roles, where they're going to ask you in a meeting to define a cost function. And all that means is you have to come up with the equation that somehow relates the cost of things. And this can be really hard and really tricky. This is not really undergrad topic, but be aware that somebody with a PhD somewhere came along and justified this in an 8-page paper. And yeah, these cost functions are kind of arbitrary sometimes, but that's what the book means. This is the definition that they're using of cost in digital circuits. Okay, looks like I got just enough time for one more example, which is good. I like throwing lots of examples of K-maps at you guys because you see them a lot. Oh, actually, we might, well, I'll talk in a second. Is okay, go ahead and solve. Once again, I count 3 implicants required. Did I already do this one? That was really funny. All blurs together sometimes. I think. Okay, I'll send out some homework on this. We'll get it assigned. You have homework due Friday that does some of that simulation. I highly recommend trying the Vivado part, but rather than right before the deadline early, so that if you need to reach out to me during office hours, you can do that. You don't want to get stuck at last minute with it.
Tomorrow.
I don't recall. Yeah, so that's the class. You guys are free to leave. I have office hours. My office is just right down there, like right now. So.
So do you know if there's any other computers, like lab computers with Vivado stuff?
This lab that's right next to us and that lab are the two that have it,
Yeah.
or you can install it on your own laptop. You could also write it in Notepad++. It actually has a VHDL option, and you can get most of your code done that way and then port it into Vivado for the final like simulation and stuff.
I use Sublime. I think there's a plugin for Sublime.
Yes, there is.
Sublime's really good.
Yeah, look at it.
That's just.
What do you write, sir? Is that really what?
I want, they just be like, your friends.
Oh, yeah.
You know, like,
Yeah, you're trying to
that I
do that.
want.
Oh, yeah.
It's like,